Hello and welcome back to this 36th lecture of Biomicroelectromechanical System. Let's quickly review what has been done last time. We talked about float zone methods for silicon production. We discussed some of the wafer specifications and preparation of the silicon wafer in industries, keeping the standards in mind. We also talked about some of the glasses like borosilicate or soda lime or quartz, and essentially glasses are nothing but combinations of some metal oxide ions along with basic silica matrix. We talked about some photopatternable glasses like Photon, which can be directly written with optics. Then we came to this introduction to MEMS fabrication area, where we talked about silicon MEMS in details, how bulk and how machining can be, micro machining can be categorized into bulk and surface based micro machining. We also discussed the detailed schematics of etching processes of substrates, wherein you do a photolithography based masking layer and use that as a protective shield for etching through silicon wafer. And then we talked about various other like techniques like subtractive etching techniques and wet etching techniques, and also some dry etching techniques, etc. We will move ahead and do some other silicon processing techniques like photolithography. So as you know, photolithography really is one of the most important techniques for fabrication of microstructures. Okay, if you look into just the lithography domain, you can divide this whole lithography business into several subtypes. You can have photon driven lithography, which is also known as photolithography. You can have electron beam driven lithography, electron beam lithography, X-ray lithography, ion lithography, so on and so forth. The only difference in this case is the resolution goes up because the ion energy is much more than simple photons. If you just look at the famous kind of de Broglie relationship between lambda and momentum, the ionic momentum increases also as a function of ion mass, and therefore you can have a lower wavelength or a higher energy or higher frequency by just increasing on the lambda. So that is why electron beam lithography is probably a high energy beam than photon beams. X-ray is even further higher, and ion lithography, because of the mass of the ion, also increases so rapidly. So therefore there is a tendency of really trying to accelerate ions through large systems, large particle accelerating systems using electric fields, and the whole idea is to generate some energy levels where the momentum is so large that you could write really at a very small resolution directly. So the photolithography process essentially is based on optics. It consists of 3 steps. There is a positioning process, there is an exposure process, and there is further a development process. If you see here, you have this wafer here which is covered by a photoresist. There is a layer, and then there is a mask which is a kind of black and white kind of feature, where you have some areas where light can go through and some where they cannot or it cannot. And then you have a shutter basically to the photolithography system, and then there is an aperture which kind of directs the light and makes it parallel from directly to the mask, and here is the light source. So you have so many things in the path of light before it falls onto this resist and changes the property of the resist by either cross bonding it or debonding it, depending on what kind of resist it has. Some of the important aspects about photolithography, especially for contact lithography, is what you call the Rayleigh criteria. Here you get this relationship wherein B, the distance between the or the resolution distance between 2 features, is also proportional to root of lambda times S. Lambda is the operating wavelength, and S is really the distance between the mask and the resist. So essentially this particular distance. In contact lithography, you have to assume the mask to be placed in consonance or facing the resist. So therefore if you are writing a feature which is already inside the resist by some distance, you have effectively some distance between the mask and the feature, which makes the resolution a little different. So B, the resolution essentially is dependent on root of lambda into S. Okay, 1.5 is the coefficient attached to root lambda S. So for projection lithography, again the Rayleigh criteria is a little different. B here, the distance of resolution between 2 particles is directly proportional to lambda times S, where S is the distance between the mask and photoresist and lambda is the wavelength, and is inversely proportional to the numerical aperture Na between the optical path. Okay. So, these are the two different criterions. Let me just describe lithography to be categorized into 3 different modes: contact, where the mask comes and sits over the wafer; projection, where the mask is far away from the wafer; and proximity, where there is a small layer of nitrogen purging between the mask and the wafer. There are different aspects of these different processes. Industrial applications require more of proximity lithography or projection lithography, because of a single issue of resist damage while multiple processing steps are incorporated. On a laboratory scale, however, contact lithography is preferable, because you do not need to develop that costly an instrumentation. The number of times you are exposing a wafer may be smaller relative to the high production industrial process. So, therefore, in industry, especially in silicon industries, there is a huge demand of optically well aligned projection lithography systems, and they are very expensive, because the optics essentially, or the optical engineering which goes into for avoiding the diffraction at very small levels is really a matter of precision, and that is what sells and is very expensive. Contact lithography, however, is the most favored process at the research scale, at the laboratory scale, and this coupled with proximity lithography makes of almost kind of 99% of the research level work that can be done using photolithography. So, let us actually look into some of the techniques where, depending, so these are the take homes essentially. So, depending on the type of energy beam, lithography techniques can be further divided into photo based, electron based, X-ray based and ion based. The patterning process with photolithography is limited only to 2D structures, 2-dimensional structures. It does not go over a certain level on the z direction of the thickness, because that is defined, or that is definable by the spin speeds and the viscosity of the solution that you are spinning. So, the layer thickness of the resist which comes up is essentially the maximum thickness up to which these structures can go on the z direction. So, it is sometimes actually called 2.5D process. The half essentially signifies that you do not have much control on the third dimension, except what you have with controlling the speeds at which you are spinning and the viscosity of the material on what you are spinning on the top of the substrate. The technique uses photosensitive emulsion layer called resist, which transfers a desired pattern from a transparent mask onto the substrate. It consists of 3 stages. Positioning process is essentially the lateral positioning of the mask and the substrate, which is coated with the resist, adjusting the distance between the mask and substrate. Exposure process is a step where optical or X-ray exposure is done to the resist layer, and it immediately transfers the pattern to the resist layer by changing properties of the exposed areas. The exposed areas are being sealed and directed through the mask, and then you have the development process, where whatever has been exposed is now dissolved and etching of the resist pattern is made in a developer solution. So, in one case where the pattern is negative tone and cross bonds on exposure, the other areas get typically removed away. In the other case, where the pattern is on a positive resist, the portions which are exposed are are debonded and they get removed away as vias and trenches essentially. Alright, so that is what this is about. Okay, and let us also look at what is the difference between the contact, proximity and projection lithography. So, essentially it is the distance at which the mask is placed from the substrate. In contact and proximity, they are very close by. Projection, where it is at a high distance for reasons mentioned earlier. Let us do a numerical example to see what is the variation. So, let us say you have a resist layer at the bottom of a 5 micrometer deep channel, which has been etched in an earlier step using a masking layer. 20 micrometer deep channel is to be patterned on this this layer 5 micrometers of resist. The photoresist is exposed to UV light and a 400 nanometer wavelength. So, we have to compare the resolutions at the bottom of the 2 channels, one where the depth is 20, another the depth is 5 microns. So, essentially what we are left with is the following. So, we have the resolutions at the bottom of the 2 channels can be estimated as, let us say, B1 and B2. So, B1 is by relationship mentioned earlier 1.5 lambda S1 as 1.5 lambda S2. So, this is 1.5 times of, you have it as 400 nanometers, which makes it 0.4 microns times of 5 microns in one case. Okay. Another is 0.4 times of 20 microns. So, essentially these are different. This is 2.1 micrometers, another is 4.2 micrometers, and these are the two different resolutions that can be achieved. So, just by going about 4 times more on the depth, you have already lost the resolution by almost 50%, and you have to only realize a higher minimum feature size by going deep down, okay, inside the channel. So, this is a problem, this is a potential problem. In photolithography and in contact lithography, if you go on higher channel depths and try to do resist processing, you will always end up with a lower resolution, and this has to be somehow controlled by guiding diffraction, guiding light in a manner that diffraction does not happen in the whole process of exposure. So, in a nutshell, deeper channels cause larger distances, okay. And effectively they also cause blurrier images. That means your resolution is lost because of going deep down. So, the resolution though of a projection system is actually dependent on the lambda as well as s, the distance of separation of the mask from the surface, but is also closely dependent on the numerical aperture. So, if you control, so there is another control aspect here. So, if you have a lower aperture value, of course, you need a higher intensity light, because lower aperture essentially is a lot of energy loss, okay. But then you could actually ensure if this value is if this numerical aperture of value is higher, I am sorry, you could ensure that the B reduces because of that, and so there is some kind of a control that is there in this particular case, okay. So, let us see what the different steps of lithography are. You are starting with a silicon wafer, as you are seeing here. You spin coat a layer of resist, right, this is the layer of resist, and then you basically set the black and white transparency mask over the resist. So, in contact mode you actually contact these two surfaces, proximity you still have a small gap in between, and in projection this would be far away from the normal resist layer. And then basically with the lensing and a focusing arrangement, you draw parallel beams of light to fall through this mask onto the wafer, and as you are seeing here, the light passing through these transparent domains or transparent regions really hit on to the surface, whereas ones which actually are blocked here due to the black or opaque portion of the transparency do not travel, and so effectively the areas exposed are just below the transparent features, and thus the feature on the top of this mask is translated on the top of this resist layer. In next go, naturally because the exposure is selective, you have these zones of different chemical compositions developing. In case of negative resist they are cross bonded, in case of positive resist they are kind of debonded, and so therefore if suppose it were a negative resist, you could etch off the remaining material away because they are still debonded with the developer solution, and you get these features which were cross bonded and stayed back. So, this is only in case of negative tone resist. The positive resist would behave just in the opposite. So, in case of positive versus negative photoresist, the only difference is that in one case in positive resist there is always a taking off of the areas which are exposed because of debonding action, and in case of negative resist they stay back, as you can see here, because of cross bonding action. That is the only difference between the two different kind of resists. So, essentially if you look at the process schematic, the photolithography really is a process wherein you start with cleaning the substrates thoroughly for better adhesion of the resist layer, spin coat a layer of photoresist, an emulsion, and essentially the resist contains a solvent phase and some other chemicals which can cross bond or debond on exposure to light by means of something called a photoacid generation. So I am going to look into that aspect in a little bit later. So once you are spin coating it, the solvent has to be evaporated so that the resist has a mechanical good strength. So you pre-bake, also call it soft bake, and then you expose the pre-baked resist to light using a masking step, and the photo exposure and the post exposure bake is carried out here at this stage, so that it catalyzes the way that the resist can set in on a surface, because otherwise if suppose you have just pre-baked and exposed, it would take some while for the photoresist to get diffusively to different parts of the resist where it would create cross bonding action. Exposure however can be pronounced and catalyzed further by application of heat, because heat actually enhances the diffusion process in the way that the photoacid generator would go through, and so therefore the post exposure bake is highly needed for this kind of a situation. Once this is done, you actually develop so that wherever the photoacid generator has gone which were exposed, they kind of cross bond or debond, and then you actually post back after the first develop, so that whatever features are remaining are firmly held on to the surface by again the heating catalyzing process, and then you can actually do etch whatever thin film you want to etch and strip the photoresist if the photoresist were a chemically sacrificial material that you are using. So some of these equipments here are used typically for the lithography. You have a CAD based layout planning, simulation and the designing center, which actually using a laser beam or an electron beam actually writes on the masking material, which typically is hard or soft masks are made using transparencies, black and white of a certain resolution, but hard masks which are also used for better feature sizes or high resolution feature sizes and used in most of the industries are made by a coating of chrome over a glass surface, which is actually laser etched or electron beam etched, and very accurately precise features are machined onto that small thin layer of chrome, and then the idea is wherever the features go away is used as a transparent part, and wherever the chrome remains is used as an opaque part, and therefore whatever translation whatever features are thus realized in this chrome and no chrome region combination is totally translated onto the resist surface. Okay. So you can use projection systems like one shown here, which has complicated optics to make a streamlined behavior of light. Mask here is much away from the photoresist coated wafer, as you can see here. And the steps for lithography occur in the following manner. You first do photoresist spin coating. This here shows such a spinner where you are dispensing the photoresist. This is the small wafer here which kind of is on the spinning table, spins at a very high rate, and then there is a thin layer of photoresist which is created. You then do the soft baking process using this kind of a laboratory oven, which is a gravity driven convection oven. You could also use a hot plate at times, and it gives more uniformity, especially while doing thick resist processing like photoresist like SU8. You prefer using a hot plate than a convection oven for better uniformity of temperature. This is what a mask liner physically looks like. You have an alignment system where there is a mask which is loaded at the top here, and the wafer which comes through this holder at the bottom, and then you could actually align them using this microscope which is at the very top here, and this can be used as a video display for whatever the microscope is seeing. There is a CCD camera through which input can go to this video display, and therefore you could actually do resist processing in this particular manner where this particular equipments can be used. Now here it shows how you are loading the mask essentially. So you essentially load the mask in the first layer of the liner here, and then you do alignment, and then you do the wafer loading here, as you can see on the lower layer. So the mask is here on the top, as you can see, and the wafer comes from the bottom layer. This is a slidable rack which slides in between this particular area where the wafer can come directly in line with the mask process. Then you have the alignment done using this microscope aperture, and then closely using this X, Y, Z and rotation table aligning the mask with respect to the wafer, and then you do the flood exposure wherein the shutter opens somewhere at a distant area where there is a light. So this whole thing is transported further right towards the exposure area, and there is a certain time and intensity which is preset. Intensity can be calibrated from time to time within a laboratory, and so the exposure makes the necessary changes written onto the photoresist surface, which after exposure can be after the post exposure bake can be developed essentially using like a tweezer to hold it, and then continuously circulating this through photoresist, as you can see in this particular beaker, while a time is maintained. You cannot overdo on the time part, so the resist starts coming off and you may have inaccurate feature sizes because of under etching or over etching, and so therefore can really you have to critically examine the development process and find out the optimum best in any photolithography, and then you can use that layer as a masking layer to etch off silicon and then take off or strip off the photoresist later on. So the way that the photoresist is normally applied in industry, and this is essentially something which is a huge automated system for process industries, silicon process industries, microelectronic industries. This was borrowed from the website on Solitech, and essentially such a technique would involve nozzle spraying, where on a continuous basis, as the wafer is automatically handled and mounted over the spin table, the nozzle automatically sprays the photoresist all around this wafer at a high pressure, so that way you could actually spin the wafer simultaneously and control the thickness. Okay. So there are some of the illustrations and schematics of how a negative tone photoresist would work, and you may also be wondering by now that what is it that causes the area which is exposed to light to be suddenly becoming sensitive and changing the chemistry or chemical nature. So I would like to give an example of this particular kind, SU8, which is a negative tone resist, as you can see here. So it is primarily an epoxy. Okay. So the way that epoxy made is like a C-O-C bond, as you can see here. So it is a triangular bond with the C or carbon sharing 2 electrons on both sides with the oxygen atom, and sharing one electron, its own electron with with itself. So basically you have a case where oxygen, which has 2 electrons here, is sharing 1 electron with each carbon, and there is a bond between the 2 carbons. Okay, that is how an epoxy would typically look like. There is a double bond because carbon is there is a single bond. Okay, and then there is also a hydrogen at the other end here, which satisfies the valency of this particular system. Now 2 hydrogens essentially. So you can represent the epoxy more like the following. So you have CHH, CHH on both sides, interconnecting O bond. The SU8 primarily is a mix of 3 such compounds. You have an epoxy resin defined as a molecule containing 1 or more epoxy groups. Like you can see here, these are the epoxy resin materials that are containing more than 1 molecular groups, which are like an epoxy COC kind of bond. You have a solvent cyclopentanone, because you have to make it fluid like so that it can flow and coat over the whole wafer. And then you have a photoacid generator, which I am going to explain just about in a minute what happens. This itself is like a photoacid generator. It is a weak acid, it is a Lewis acid, and it actually protonates on exposure to light. Okay. So wherever there is a light exposed to this kind of material, it will certainly formulate into a proton H plus, and the remaining compound which becomes negatively charged. Let us look at what happens to this protein, or how does the photoresist work. So if you look at this particular figure here, you can find out that the process really begins with an exposure to UV light in certain selective areas. So this right here is an illustration of the photoacid generator H plus SBF 6 minus. This is a demo photoacid generator. On exposure to light, it would immediately release the proton, and so the proton goes and opens up the epoxy chain in the following manner. So the first step is carried out by a positive charge onto the oxygen and the hydrogen, formulating a bond with the oxygen. The second stage is maneuvered by the very fact that there is a lot of hydroxides, like with an R1 or an alkyl group along with it, and so they are ready to donate the hydroxide and bond this R1OH, the alcohol which is there along with this particular configuration. There is a high energy bond with a positive charge, so this bond opens up and you have R1OH with a plus charge on one side and R1OH here with no charge. Okay. So therefore this is how the Lewis acid giving a proton plus has already formulated or opened up the epoxy ring from a triangular orientation into some kind of a a double alcohol compound which is formulated here. and in the third step essentially what happens is that this H plus comes out as a proton and again mixes up with this photoacid generator S plus H plus SB F6 minus. So, H plus here or this whole compound here is nothing but a catalyzer. It does not itself participate in the reaction, but let the reaction carry forward by opening up the epoxy stage, which is a very essential intermediate step in this particular reaction. So, once this happens, then you are left with a bonded structure like this. Now, you can assume that you have other epoxy rings which are close by, which will bond to this kind of a structure because it has a OH group, and so therefore slowly this whole structure is kind of cross bonded and formulated by bonding to each other. So, therefore, wherever light falls and photoacids generate the H plus or it becomes a Lewis acid, it automatically starts the bond on the different epoxies, and there is a growth cycle of these bonds happening in all the 3 dimensions, but confined to and only confined to the area where the light is tailoring the photoacid generated to give the hydrogen ion or the H plus. But because it is a diffusion driven process, there are problems, and one of the problems is that because you do not have a control on the distribution of this photoacid generator, although it is pre-mixed in a very fine manner, but spinning sometimes lets the photoacid generator moves away from time to time. So, therefore, you have to really optimize the exposure time, you have to optimize the exposure intensity. So, that whole thickness of the resist is having all these photoacids initiated and generated, and whole thickness is basically having the cross bonded structure available. So, the Lewis acid primarily is responsible for protonation. It opens the epoxy ring, it polymerizes with another such open ring and formulates another alcohol which further polymerizes with another open ring. This way wherever there is a Lewis acid formulation, the 3-dimensional network establishes itself. Now, I would like to bring your notice to several of these experimental results which I personally have done during different parts of my research experience. Here, as you see, this is the time optimization technique that we are having. Basically, we are trying to optimize an exposure time. So, we wanted to build up a feature which is about 50 microns thick, like this, let us say this depth here or this width here across is about 50 microns or so. So, really if you look at different exposure times like 30 seconds, 50 seconds, 100 seconds, 150 seconds and 200 seconds, you see that the edges are slowly turning from curvy to flatter and with the best resolution which is available at 150 seconds. Now, what happens before this is definitely the exposure is inadequate to send enough number of hydrogen ions to cross bond, and therefore, this structure here, the roughness really eats away into the 50 microns, it eats away into the 50 micron structure, as you can see. Now, this gets a little better here because probably the time of exposure was a little more, so a little more number of H plus was generated and it could actually correctly, although not totally correctly, formulate the edge. So, the edge keeps on increasing its straightness as the exposure time is increased and more amount of hydrogen ions gets generated, after which this is the optimum best, after which suddenly the reverse effect happens. So, this in fact is much bigger than it is a 200 seconds, it is much bigger than 150 second, which is actually equal to about 50 microns. This may be bigger on account of the fact that additional H plus ions are generated here because you have overexposed the resist material, and so the additional ions would diffuse and create a very rough edge in the positive direction. That means this feature size effectively broadens out because of that. Maybe the 150 was just near about this, and this is broadened out by several more microns because of additional hydrogen ions which diffusively sneak past the edges of this particular configuration. So, if you look at on the average scale, really there is an optimum best of the average roughness which is about as less as about 4 microns or so. Beyond it, photolithography is not sometimes able to do its job properly, even if you are using a hard mask. Okay. So, after doing photolithography in great details, let us actually look at some of the deposition methods and basically the surface micro machining methods. And so, the first technique which comes to mind is metal evaporation process. Now, this is a very conventional, very old age old technique where you are actually creating a crucible where you have some metal wires like maybe platinum wires or gold wires or titanium wires or chromium wires, and then you are actually suddenly evacuating this chamber, sending the gases outside this chamber and heating. So, this is actually a wafer holder or a wafer boat. Essentially it is made up of tungsten and something like this. You have If you look at the overall feature, it is something like a small boat like this on both sides, where your tungsten material is kept inside, the wire is kept inside, all folded and jumbled. Sorry, the material which you are trying to deposit is kept inside, and the tungsten is a very highly resistive or has substantial resistivity and substantially lower on the temperature based resistance variation scale, and also it can withstand high set temperature values because of its high melting point, which is about 3400 degrees Celsius. So assuming some of these data, if you have a wire which is of a lower melting point, you can of course red heat this tungsten wire so that it is just about lower to the melting point and still in formulation of a solid structure, and in that case the heat which is delivered is good enough to evaporate all this material out from the crucible all into the atmosphere, and this is high vacuum. So therefore there is no chance of contamination, and the high vacuum is created essentially by two mechanisms. One is the roughing pump, which would actually go up to about, let us say, 10 to the power of -3 torrs or so, and the remaining would be taken care by this diffusion based pump, which has roughly a backing pump, okay, and a cold trap. So essentially the way the diffusion pump, if it is an oil diffusion pump, would work is in the following manner. So you have these fins, okay, at different levels, and on basically both sides of the wafer, and you have oil vapors which actually go into this particular area, alright, and absorb whatever is and so there is a high vacuum pull on this direction. So the oil vapors which are left here in this area kind of absorbs whatever little bit molecules are left over in the chamber after the roughing vacuum has been achieved, and takes the absorbed molecules along with it back to the roughing pump. That is the way the oil diffusion pump really works. So therefore it can attain a finer vacuum level of, let us say, about 10 to the power -5 torrs or so, and in this vacuum it is sufficient to create a clean process where there is no oxygen or nitrogen inclusion within the silicon. The substrates really are mounted on the top. As you can see, there is a series of substrates here which are rounded off and just over the target in the vacuum chamber, and these wafers are deposited with the metal on the top, and you can do a sacrificial layer in photolithography so that the deposition gets in a normal way. So the evaporation deposits a thin film on the substrate by sublimating a heated source in vacuum, source material in vacuum. The vapor flux from the source coats the substrate surface, and based on the various heating sources, the various evaporation techniques are vacuum thermal evaporation. You have another technique called E-beam evaporation, where the same process is done by heating this with an electron beam. So you have a high voltage electron beam which is pumped at a high energy onto this target material, and it sputters off the target, and vapors are created within the vacuum in which all this process happens, and it goes and physisorbs on the surface of the wafer, okay. And then there can be other techniques or other means of heating for depositing the vapor of the metal on the top of a silicon substrate. You can also deposit alloys using this by using 2 or more materials conveniently in a certain ratio. In this case it may be a wire made up of alloy, or maybe just by percentage weight you could do the 2 metals as globules and put it inside the crucible and then evaporate them together. But then it will also be a function of the relative melting points of the 2 metals, which one floats earlier and which one melts earlier and vaporizes earlier and which one vaporizes later, okay. The idea is to quickly go to a temperature in that case where both the phases are vaporized, and one is more vaporized based on the fact that you have lower amount of melting point, so that ratio would be maintained. Another very popular deposition technique is sputtering based deposition technique, which is actually a plasma driven process. So here in this particular illustration, as for example, the sputtering process is carried out under with a plasma under low pressure of as low as about 5×10 to the power -7 torrs, okay. And this process involves low temperature, which is contrary to CVD. Plasma really is a state of ions and electrons. Here what happens is you have these 2 electrodes which are also responsible for generating the plasma. You pump in argon in this type of space here, which is at a certain pressure, and the argon generates argon ions and electrons. As you can see here, it generates argon ions and electrons, okay, and then you actually drive the argon ions to the substrate as you can see here, and both the target plates are kept on both sides as you can see here in this particular case, and then this particular electrons and argon ions which are generated are slowly able to, if you put a bias onto the system such that this plate is made positive and this is made negative, the positive ions would hit this target and the negative electrons would hit this target. Let us suppose we drain the electrons away. So, the positive ion, as you can see, the bias is outside here, the AC bias, okay. So, the positive plate and so the positive plate changes between both time to time if it is an AC bias. If it is a DC bias, it will only be positive on one and negative on another, but whatever happens brings a substantial amount of ionic momentum on both the plates, thus physically ablating the material off. So, if this target is platinum or gold, it will ablate the platinum or gold materials or atoms off the surface, and then the carrier gas would essentially drive this more towards the substrate, which can be given a slight bias so that you can hit with the carrier gas the material onto the substrate of the electrodes. The gas is too evanescent to kind of escape, but the material once deposited would be kind of embedded onto the substrate surface, and it has high energy impact based on what this bias voltage can be really made. And so therefore, this is another way of transporting material from these substrates on both ends onto the surface of the targets on both ends onto the surface of this substrate material. So, in a nutshell, the plasma is made up of positively charged ions and electrons, can be produced by high voltage DC sources, RF sources, or by fluctuating magnetic fields created by inductive coupling. The positive ions of the metals in the inert gas or argon gas carrier bombard the surface of the target at such a high velocity that the momentum transfer on impingement causes the metal ions to evaporate, and the metal vapor is then led to the substrate surface and is deposited after condensation. Okay, so after doing this sputtering methods, let us actually briefly discuss what these can be, the e-beam evaporation or the vacuum evaporation or sputtering can be used for. So, the best way of using them in microelectronics or MEMS is deposition and liftoff, wherein basically metal circuits or metal conduits are fitted within or over a sacrificial mask made up of positive tone resists. Here for instance is one example. You have a silicon wafer here at the bottom, which is coated with a layer of photoresist, which is this layer here, which is slightly red. Okay, so this is the positive tone photoresist, and a selective feature is etched by photolithography and developing process, and now you are exposing this first to a vapors of titanium and then followed by vapors of gold. So, you have to really be careful in this about the interlayer adhesion. So, if you are depositing something like gold, you may have to use either a titanium or chromium layer for building an intermediate which can bond effectively to the silicon dioxide on one side and the gold or the parent metal that you want to deposit finally on the other side. So, it creates a kind of ligand kind of system or framework to retain a good adhesion between the deposited film and the surface. So, you have something like an intermediate layer, and this layer does not go really above a few tens of nanometers, about 10 to 20 nanometers, and then this layer can go as high as about 500 nanometers or so. Of course, it is very thick. Beyond that, you need to use plating methods, electroplating methods, because the rate of deposition is very small, and you should not cross a limit where the photoresist surface can be damaged. So, once both these are evaporated, and this can be found out from this yellow line here, the areas which are really trenches or vias have these deposited on them, and then you can remove the resist layer and you can expose this metal deposition on the top of this etched surface of silicon and this method is known as liftoff. So, whatever photoresist here can be laterally etched using some kind of solution like acetone, etc. However, the portions which are adhered onto more firmly onto the silicon substrate remain, and the other layers of the photoresist go off because of the development. So, this process is known as liftoff. Finally, you are left with a feature or a conduit made up of metal on the silicon wafer. So, you have an etching process followed by a deposition and liftoff process here. Let me show you some of the examples Like for example, this essentially is excerpt from my previous work where we are showing a set of interdigitated electrodes made with platinum metal with a titanium interlayer in between. So these can be mostly used for IC interconnects. In this case it is used for a BioMEMS device, as I will be discussing later in the part where I will be doing a discussion of the research area essentially. These are some more microscopic images of patterned metals, as you can see, and this has been characterized under a microscope. The terms here north, east, west, south is really indicative of what portion of the wafer we have taken these photographs, and they have been photographed or imaged in different areas, and you can see that the quality of the deposition process essentially is just replicating what feature was there on the masking surface, and this essentially, this finest line here is of the size of about close to 50 microns or so. So that is how small this feature is, and this is about close to about 2 mm by 2 mm essentially. Alright, so this is how you can use successfully deposition and liftoff to realize any kind of patterns or features onto the surface. Let us talk about another new area which is related to how you can introduce defects which can be group 3 or group 4 inside silicon material. So this is also known as doping and ion implantation, and why is it needed though is because, as you know, the semiconductor can be P or N type based on whether you have an excess whether the metal belongs or the dopant belongs to the group 5 and you have an excess electron that it can share with silicon apart from its regular 4, and if it is to the group 3 you have an excess hole which is a devoid of electron, which is a vacancy, and essentially as the electron hops between the first to the second atom, the vacancy shifts in the opposite direction. That is how you look at it. So one is a P type, one is an N type being the group 5 dopant doped matrix, and group P type being the other way, that is group 3 doped matrices. So how you do the deep dopant is or doping is essentially through using something called an ion implanter, and here essentially there is an ion source which can generate from a gas phase a beam of ions, positive ions typically, and then they are accelerated through an electric field, okay, and it reaches this coil here which is a magnetic coil, and it can actually, based on Lorentz forces, deviate this into different tracks. So if you are essentially looking at maybe several ions coming together, they have different forces that they feel on each other based on Q times of V cross B, right. This is the Lorentz force. So essentially Q is the charge on the ion, V is the velocity of the ion, B is the direction of the magnetic field. Assuming the velocity, the B remains constant, okay, the magnetic field remains constant, and the velocities are different, okay. So essentially when you are accelerating an ion of a heavier atom or a small a lighter atom under same electric field, the accelerations that they gain may be different, which is essentially the electric force Fe divided by the mass of the ion. So this is essentially Q times of E times of mass of the ion. So if your charges are same and the masses are different, so the accelerations could be varied, A1, A2, A3, so on and so forth, and if the accelerations are different, the velocities that these attain at a particular instance of time will also be all different. And so therefore, assuming there is an ion flux coming out of this chamber, of this electrical chamber here with the high electric field, and coming on to this magnetic field, you have different values of V, and so you will have different deflection forces, and so you can actually split up ions based on that, and the heavier the ion is, the lesser it will deflect, okay, and the lighter the ion is, the more it will deflect. But the idea is then you can actually separate ions on the basis of sizes, and you can have a particular ion go past this tube which has the target at the very end here. This whole system is carried in vacuum, and this target is kind of implanted with the particular ion which is filtered off this magnetic field using Lorentz force. So therefore, the ion implantation technique is one of the most important techniques for microelectronics, adds impurities, the semiconductor in a nutshell. In ion implantation, ionized impurity or atoms are accelerated through an electrostatic field and strike the surface of a wafer. The dose can be tightly controlled using ion currents, and doses from process ranges from 10 to the power 11 per centimeter square for very light implants to about 10 to the power 16 per centimeter square for low resistance regions such as contacts, emitters, buried collectors, etc., as popularly done in transistors. Okay. And by controlling the electric field, the penetration depth of the impurity atom can also be controlled. So, you can see up to what extent you want to make it into a P plus or a P double plus or a N minus, so on and so forth. And by controlling the electric field, the penetration depth of the impurity atoms can vary, it can be made smaller or bigger. You have also the gas phases which are used typically for these purposes, like trifluoroborane, this is arsenic hydride, this is phosphine or phosphorus hydride, and these two, as you know, are group 5, this is group 3. Essentially they are commonly used gases for both P and N type impurities. Separation by implantation of oxygen can also create what you call silicon metal oxide features, SiMox features, or SOI, silicon on insulator wafers. So, this is how the doping in the ion implantation process really goes. Let me also talk a little bit about a very novel and a very interesting process called Microstereo Lithography, which has been translated very effectively to build 3-dimensional microstructures, especially by groups up at UIUC or so. So, this particular technique, Microstereo Lithography, is also based on kind of section by section 3-dimensional writing. For those of you who are already aware of the process of rapid prototyping, the machine RP was developed with an intention of really making a complicated geometry. Let us suppose you want to make a mold for something like the femur bone of a particular animal or maybe human beings, and normally such a shape, such an irregular shape is very hard to machine. So, what people formulated was what you call RP or rapid prototyping, where this bone structure is taken on a CAD drawing, okay, and then it is sectioned into thin pieces or thin sections, and each section is made thin to an extent so it is an uniform cross sectional area. Okay. So, there is not much of depth involved in that, and then a polymer melt is essentially used to write. So, therefore, the spray of polymer is done in a manner that this polymer melt is used to write over a surface in a manner that layer by layer the whole shape can get built up, and then there is some kind of melting where the glass transition temperature would be reached, and then some fine polishing is done for the final feature to be realized. So, it can really generate very good 3-dimensional features with great accuracy and precision if you could really traverse the nozzle head in a exact parity with the CAD drawings, section by section CAD drawings. So, that is what an RP technique normally does, rapid prototyping. Stereolithography or microstereolithography is exactly the replica of that process. Only factors in the medium that in which you are actually writing is based on photoresist. You are exposing the photoresist and trying to simultaneously cross bond the material as you keep writing layer by layer. So, here for instance is an example where photolithography, this microstereolithography is done. So, as you see here, there are two ways of doing it. So, microstereolithography can be categorized into single photon or 2 photon type of lithography, where you have slightly different nature of these processes based on their exposure methodology. So, here as you seeing, this is a plate which is actually moving from the very bottom of this liquid resist here. This is actually all liquid resist, and it is going towards the top, and the beam, the UV beam which is used to write on the top of the resist is focused in a manner that it goes to various focal depths. So, in one instance it is focusing on to this surface, in the next instance it will be focusing on maybe a little bit down, the next instance further down, next instance further down, and so on and so forth. So, the beam essentially is been focused at different regions of depths within the liquid resist. So, as this writing process continues, let us say this is the first section of the overall feature. So, you are actually putting this this plate very close to this feature and then starting to proton write or UV write on the top of this, so that you have cross bonded this area. The plate moves a little bit further up here, and so the idea is that the resist which is not bonded and around it kind of flows because of hydrostatic pressure in this region. Once it is completely filled, you again write this other part, the second cross section on the top of it, then you write another cross section on the top of it, and so on and so forth till you actually come towards the end, and the whole feature is realized into several blocks of different sections of the feature. Now, you can also use the same technique by putting the laser beam in the opposite direction and start writing more in the top down manner. Okay. So, you go selectively from top end to the bottom end, as you can see in this particular illustration here. Okay. So, the idea is that you are actually writing whatever feature you want to write by sectioning into thin pieces and writing exactly along. So, the laser head which actually focuses the light also is CAD defined, the path is defined by the CAD package, the cross sectional area that you are defining onto the Micro-stereo lithography system by the CAD package. So, if you want to increase the throughput of the process, this is typically how it would look like, and so therefore always there is also a motion of the XYZ stage which is containing this resist, which actually ensures that whatever two dimensional features you are wanting to imprint on the surface is getting imprinted because of this XY motion. The control unit also controls the UV source, the focusing arrangement, Z stage for that, and the XY stage, Z stage parallelly, and this all is defined by the layer by layer programming that is made onto the CAD package to do the complicated shape, to realize the complicated shape. You can make this process high throughput. This is typically, this mechanism is a very low throughput process because you have to generate so many different features one at a time, and as you know, in the micro world, the feature intensity, the feature density is really very high. So, you may have to independently write all the features in this kind of a process, and it becomes extremely time consuming or very low throughput one. So, people have used other methodologies, including some things like this, where you have multiple fibers as you are seeing, which takes the light onto different places where you can write all at a glance, all at once, and you can parallelly write many features instead of one. Another very interesting mechanism that a group of UIUC had actually developed is by introducing something called a digital micro mirror device, DMD, or a projector, to kind of use the light or shine the light onto a microscope by defining a digital image onto the projector. Okay. So, the idea is the mirrors will turn off on and off the pixels, and then only a portion which would be corresponding to the whole feature would glow up together, and this can be translated down to do stereolithography, and that way very fine three dimensional features can be resolved at a very fast rate because of this digital micro mirror device. So, various intelligent processing techniques have been used to modify the microstereolithography process so that you can actually develop a lot of interesting micro scale features on the surface. So, let us look at some other processes, some other microfabrication techniques. This, for instance, is thermal oxidation. It is basically used whenever you want to develop insulating oxide layers onto the top of silicon wafers, particularly for doing a proper insulation bed or providing a proper insulated bed for electrode layout. Like for example, the interdigitated electrodes that you saw in the earlier example in sputtering were made over a silicon dioxide surface which was thermally grown. Now, thermal growth of oxide is essentially a diffusional process. So, the silicon dioxide grows at the cost of pure silicon. So, pure silicon, essentially the oxygen ion diffuses through the lattice or creates an oxide layer because of the diffusion. So, you have a thinning down of the overall pure silicon and a thickening of the silicon dioxide or the wet oxide on the top. So, silicon dioxide is deposited with CVD or thermal oxidation. So, there are two different kinds of oxides. One is a dry oxide, which is essentially done by heating the oxygen at a temperature of 800 to 1200 degrees Celsius. You can also carry the oxidation process by wet oxides, wherein you have the gas or the oxygen passed through or bubbled through heated water. which kind of moistens. Okay. And so the temperature also again required is the same, but in this case the oxidation is much more faster, and the wet oxides typically grow in much lesser time in comparison to the dry oxide. So if you see here in the figure, you can actually find out that there is this set of resistance heaters on both sides, and this is a quartz tube where you have a gas supply which can be a wet oxygen or a dry oxygen, and this is going towards the vent side. So the gas inlet is from the left end here and the gas outlet is from the vent end. This essentially is the wafer boat. It is also made up of quartz, and there are these aligned wafers on the top of this particular illustration here, and as you heat this wafer to a certain surface, there is always a thermal motion or movement of the atoms on the surface, and then you flow oxygen. So there is a capture, rapid capture of oxygen moieties over the whole surface, which develops finally the oxide. So there are different models to explain the different growth kinetics of oxygen, which I am not going to look into at this time. However, and we are kind of towards the end of this lecture. So next time onwards we will just talk a little more about microfabrication, some of the processes which are left over today, like how plasmas can be generated, or how gas plasmas can be used to modify surfaces, including etching, and then chemical modification, so on and so forth. So with this I would like to close the lecture. The final lectures would be on the basis of some research papers which have been done earlier based on some of the concepts that we have illustrated throughout the length of this course. Thank you.